In this second day of the short course on molecular dynamics, simulations, techniques, and applications, or I forget what I called it, something like that, I want to dive a little bit more into aspects of simulations that we avoided in the first exposure to the anatomy of a simulation and so on, which is where some of the various pieces come from. So some of the things that are hard to create for simulations, namely the potentials, the interactions that one must specify between all of the atoms in an atomistic simulation, so all the bonded and non-bonded interactions. The topology files, which you'll remember specify the kinds of atoms that are present in a molecule and how they're connected, and by implication, how they interact with all the other atoms in the system. And finally, initial configurations, which I alluded to the fact that sometimes they're a little bit tricky to build because it's rather hard to build a realistic, densely packed, but not very well ordered structure. And so how do you do that? And the answer is you don't. You do it some other way. So first, potentials. So fortunately, we are operating in a time when quantum chemistry calculations are quite powerful and effective in computing the interactions between molecules. With an asterisk, okay? Quantum chemistry can compute potentials, it says, but there's a point to be made, as I'll mention in a minute, an important limitation. So what were those potentials anyway? Well, you remember that part of it was Coulomb interactions, and one represented molecules as, you know, point atom positions, and each of those atoms would have a partial charge, right? So water, which is neutral, of course, nonetheless has a charge of something like 0.8 minus 0.8 on the oxygen and roughly plus 0.4 on the two hydrogens. Where do those come from? Well, one place that they can be got is by calculating using quantum chemistry packages like Gaussian, a best fit point charge for each atom, and best fit to what? Well, best fit to the electrostatic potential in the vicinity of the molecule, someplace on the space-filling surface, because that's where other molecules can get close to at normal temperatures and pressures. And so you can't possibly fit everything about the electrostatic potential of a cloud of electrons around point-like nuclei, but you do the best you can. And so you want to fit the sort of charge distribution that is electrostatically relevant for nearby molecules. So you do that, and that's a thing in Gaussian. Also, bond and angle and dihedral potential. So every pair of atoms that are bonded, two carbons in a hydrocarbon chain, have a quite stiff spring between them with a very well-defined rest length and a big stiff spring constant, and it's a rather harmonic interaction for the small kinds of deviations that you're going to have in sort of ordinary temperature situations. Angles, again, roughly harmonic angle potentials about some preferred angle for different bonded triples of atoms, and dihedral potentials, which are a little trickier because they're quite soft, and so it's possible to rotate molecules about bonds through the entire 2 pi, and so the potential is not well approximated in that case by harmonic potential, and one has to fit that to some periodic function, typically a sum of cosines. And I'm going to describe in a moment how one goes about calculating those using Gaussian. And I'm going to sweep a few things under the rug, which I'm sort of reminding myself with these last 2 bullet points, about which I won't say anything right this minute. But what about the asterisk? The thing I haven't mentioned in talking about potentials that you'd like to compute using quantum chemistry, but you can't really, are the van der Waals interactions. You know, every nonpolar everything has some polarizability, and two molecules at a distance interact via their dipole fluctuations in what we call dispersive forces or van der Waals attractions. And those, unfortunately, involve not just the properties of the ground state, but fluctuations into the excited state. And it's not an easy thing to compute that contribution for different atoms from simple quantum chemistry calculations. And that's a limitation of a present limitation of using density functional theory type calculations, which are really about the ground states of molecules, to compute those attractions. So how do you get those? Well, that's where the blood and sweat and toil of countless graduate students comes in, because remember how the potential we're using is called OPLS, optimized potentials for liquid simulations. Somebody optimized those, and the thing that they optimized, a lot of what they optimized were the attractive interactions in order to get the densities and cohesive energy densities and boiling points and stuff like that of a whole series, hundreds of organic liquids. And so that is one of the dark secrets of atomistic simulations. Is it's a pain to get the van der Waals attractions right. The repulsions you can kind of get because they have to do with, you know, atoms not wanting to overlap, and quantum chemistry calculations know about that pretty well. So that's not so hard. But the attractive part is sort of a black hole. Anyway, so what about these scans? Well, here's sort of a picture of what you might like to do. There's butane. Yeah, butane. And there's a central carbon-carbon bond, the thing marked with red. And so it's got, as I said, a harmonic spring with a length that's quite well determined and a pretty stiff spring constant. So what you might like to do is to calculate the energy of that molecule as a function of that bond length, varying it a little bit around its minimum. And so that's what the graph at the lower right-hand side has done, using, as I said, the quantum chemistry package Gaussian to do it. And the text over on the left is the input file that was used to do this. So just as a summary, you can represent the geometry of molecules in a couple of different ways. One would be to just say where all the Cartesian coordinates are. Another way, often used in quantum chemistry calculations, is to give what's called the Z matrix. That means here's an atom, here's another atom at a certain distance. What direction? Don't care, I've only got two atoms. Here's another atom, a certain distance from this one and an angle from that one. And here's another atom, a certain distance from this one, angle from this one, and dihedral from that one. And you build the thing up in terms of these internal coordinates. And that's what that matrix is on the left there, just under the 0, 1. It's the list of the atoms, the atom it's bonded to, the length of the bond, all given as variables. And then there's a length, and then all those variables are given values down below. And so B7, that's the bond, that's the red one, is not just a number here, but is starts at 1.5, takes 10 steps of 0.01, and that's how the scan is done. And everything else about that Z matrix is held rigid, so this is called a rigid scan. So it just pulls it apart like this and leaves everybody else alone, and there's no optimization done, and you get this nice curve. So that's a rigid scan. I see there's a question. No. Okay, not a question. So that's a rigid scan. Similar sort of thing with an angle scan, and I should remark that, you know, there's a sort of a hierarchy of energies in distorting a molecule. Bonds are really, really stiff. Angles are pretty stiff. Dihedrals are soft and floppy for single bonds, not for double bonds. Obviously, it's very hard to rotate around a double bond. So the angle scan is a similar thing. I'm now going to rotate. I'm now going to vary that that red marked angle a little bit around its roughly tetrahedral value. It's not quite but basically tetrahedral. Um, and that corresponds to angle A6, which starts at 110, as you can see in the red highlighted remark down at the bottom, takes 10 steps of 1 degree. And then you get this nice energy curve. And again, you don't touch any of the other coordinates at all. And so these calculations are relatively cheap to do, and you can get decent values for angles or bond lengths that are not in the extensive, but of course not infinite database of pre-existing bonds and angles and so on. Finally, dihedrals, as I say, are soft degrees of freedom. And there is the central dihedral of a butane molecule. And in this case, I've done something a little different, which is a relaxed scan. That is, I'm going to rotate around that dihedral, but I want to optimize basically everything else. So if the hydrogen atoms need to shift around a little bit as I spin this dihedral, they're going to do that. And I don't want them to bump rigidly into each other. I just want to know about the gentle potential that I get if I turn this thing. And so the text, for how to do that is over on the left. Those input files are, not very complicated. And the resulting periodic potential is the trace at the lower right. And you can see that the potential is indeed soft. Okay, this energy is in kilojoules per mole, and you should have maybe tattooed on your brain someplace what KT is at room temperature in kilojoules per mole. And the answer is 2.5. So the trans-gauche energy difference, right, between the central minimum, which is the trans minimum, and the two minima off to the side, which are gauche plus and minus, is KT.5 or something. And so that tells you this is soft, right? That your molecule is going to oftentimes, just from thermal excitations, be in the gauche plus or minus at room temperature, right? Butane's not always trans. So from those things, you can get angle and dihedral and bond stretching potentials. Getting angle potentials is a little bit tricky sometimes because the angles are coupled together. So if you imagine taking methane, okay, so here's a carbon and tetrahedral hydrogens. If you open one of the HCH angles a little bit, you can't do it without changing other ones, right? Just because of the geometry of the molecule. So if you've got all the HCH angles in your potential and you open one of them, then some of the other ones kind of get opened as a side effect as you scan that. And you have to take that account. You have to take account of that when you're fitting the spring constant of that angle. But that can be done. So that's bonded potentials. And as I say, non-bonded potentials are everybody pointing at everybody else for saying, well, we borrow this one from this molecule and we borrow that from that molecule, and ultimately you're adjusting them so that you get sensible densities, sensible kind of near neighbor distances between groups, sensible boiling points and stuff like that. And then basically it's a mess. So that's potentials, and our group suffers a fair amount every time we introduce a new molecule with trying to, with worrying about this stuff. But it's absolutely essential if you want your movies of real molecules to mean anything. And for particular applications, particular things are very sensitive. So for instance, if you're simulating polymers and you don't get the dihedral potential right, the polymer will be too stiff or too flexible, and its geometry in the melt will be wrong. And anything that cares about that, like how entangled it is or what kind of friction it has when you drag it out of there, or things that we care about, will be messed up. And if you don't check that stuff, nobody knows. Okay. So so next, well, building topology files. We used PDB to GMX for that, for the protein molecule, and that was a tool built again, by biochemists and biophysicists who want to be able to simulate proteins. And so Fortunately, proteins are built from only 23 repeating pieces, and so it can, the information to encode what's connected to what for those pieces can be written down piece by piece, and that's more or less what PDB to GMX is using, what are called the residues, right? The monomers, if you want, of the protein. There's a residue file that describes how each one's connected, and a program that generates all these bonds and angles and dihedrals, just by looking at, what's connected to what, and therefore what's connected, one bond away, and so on. That's what the program does. In general, building a topology file is kind of tricky, and if you go hunting on the internet, you soon visit a world of pain of graduate students who are like at sea, and I need to build a topology file for such and such a molecule. How do I do it? And and people with experience are kind of responding, well, so the strategies for that are several. One is you borrow. Okay, you hope that somebody has been interested in your molecule before. And a very nice website, for example, is one called virtualchemistry.org, which has an archive of close to 200 different organic molecules with topologies that they've tested. They've simulated them as liquids, they've checked against the densities and stuff like that. And so they're pretty believable. It's a terrific resource. Another possibility is to try to write a program that automatically generates the topology file, not using PDB to GMX, but using chemical knowledge. You give the thing a chemical structure in the form of a PDB file, but not a protein, and it looks at it and tries to figure out what kind of atomic group is present. So not just an oxygen, okay, but a carbonyl oxygen or an ether oxygen. Not just a carbon, but a CH2 carbon or a carbonyl carbon or an aromatic benzene carbon. I mean, these are the kinds of things it's got to figure out. And so there's a Russian website that is reasonably successful at automatedly generating topology files from PDB structures, and we use that a fair bit. A third way is to do it by hand, and you draw your molecule and you use chemical intuition. And you say, okay, this piece looks kind of like this piece of that molecule, and let me borrow that part from some molecule that's in the virtual chemistry website, and so forth. And you can assemble something plausible that way. And we often do that, for smallish molecules or groups that we don't have structures, we don't have topology files for. And finally, we can piggyback on to the work done in PDB to GMX, and this is particularly useful for polymers and linear molecules, because it turns out that you can add residues to the residue file, basically invent new monomers. And those monomers don't have to be amino acid monomers, okay? They can be basically anything that chains together, and if you follow the syntax of how those files are built, then you can use that plus a well-constructed, well-labeled PDB file to make a topology file for a polymer or an oligomer or something like that. And you're going to see a little bit of that in a little while in the last example that we do for Deckhane. But we use this routinely to build topology files for polymers. Right. So so what are these RTP files? These residue in fact, I'm about to show you now kind of how that works. What do these residue topology files look like? Well, so here's where's my mouse? Oh no, I of course I can't go there. That's the one shortcoming of this way of sharing is you can see the screen just fine, but I have no pointer. In the upper right, you see a central monomer or repeating unit of polyethylene. So it's got two carbons, C1 and C2, each of which have two hydrogens, and the C1 is bonded to the previous C2, and the C2 is bonded to the next C1. And that's what that little piece of file over there, PEM which stands for, when we made this up, I mean, whatever, polyethylene middle. It lists the atoms, gives them specific names. It tells what kind of OPLS atom they are, okay, which are the alkane carbons and alkane hydrogens, what their partial charges are. Okay, you can see the hydrogens are a little positive, as they are, the carbon is a little bit electron withdrawing off of the hydrogen. That covalent bond's not quite symmetric, so there's a little bit of a partial charge on the hydrogen. And then it lists the bonds, but only that. So you don't have to list the angles and dihedrals and stuff. That's what's in a residue topology file. And then PDB to GMX does the rest. If you construct a PDB file, that is a molecule configuration file, that's labeled exactly the same way, with the monomers, with the residues called PEM or whatever, and the atoms named exactly the same and in exactly the same order. And that requires, editing the PDB file, which if you made it in Avogadro isn't necessarily labeled that way at all. And for a long molecule, that's a pain because you got to shuffle and shift around all the atoms. And, it might be hundreds of atoms long, and that's an unpleasant job, best done by an eager undergraduate. Not something you want to be doing yourself. So we try not to do it that way. And what you can do instead is to build long PDB files from short little pieces. And so we've written a script that does that. And essentially what you do is you make little pieces, and you can see 3 little pieces for polyethylene down there, the beginning, the middle, and the end. And they're all lined up in just the right way so that if you stack them up like blocks, they would stitch together to make an all-trans piece of polyethylene or deckhane, for example. And so we used one of the GROMAC's tools, which is called insert molecules, to stack these things at just the right distance so that it builds a build chain. And the individual PDB files for those monomers have had their labels changed in such a way that it works out, so that when you stack it up, it's in exactly the right order for PDB to GMX to work on. So it's little things like that that you have to do because there's no tool that's like build me a polymer and make a topology file for it. And then this is the solution that we've come up with for doing that kind of thing. So that little script you'll use in this example. And so as I was saying, the monomer structure in the PDB file, which is down there at the bottom of this page, matches in the names of the atoms, and the residue being called PEM and stuff matches the residue topology file entry. And that was edited by hand. This thing was built in Avogadro and oriented the right way so that it'll stack up, and then labeled, changing that file by hand. Yeah. So, so that's the kind of thing, the various dodges and so forth that we use in order to build molecule ITP files that are both chemically realistic in terms of having the right kinds of atomic groups and also the right kind of structure. Right. So, so let's talk a little bit about building configurations, initial configurations, which can be challenging. So we saw in the lysozyme example, that there exist tools for solubilizing something, that is for packing water around a thing. And the thing could be, a protein in solution, or the thing could be a nanoparticle, or it could be, a Bucky sphere or something. I mean, those, would aggregate in water, but you can simulate one of them or 2 of them in water just fine. Or if you want to make something like a salt solution, then you can do that using solvate and GenIon for changing some of the waters into ions. So there's tools for that. You can also use this insert molecules thing, which will allow you to insert molecules at specified places, to insert them just randomly in the box and keep trying until it succeeds to do a certain number of insertions, or it runs out of tries. You tell it how many times to try. So it just inserts them randomly, and then according to some, heuristic about overlapping, accepts or rejects the insertion. And that works pretty well if you're trying to insert things that are round. It does not work very well if you're trying to insert things that are sticks, because the sticks will inevitably whack into other sticks with high probability. So, round things, it works pretty well. Regular insertion, building things by stacking, is easy to do, and so one can build ordered structures like crystals by building a unit cell and then stacking that up to some size. So suppose what you want to do is make a melt of deckhane, or a melt of polymer, of oligomer, chains that are 20, 30, 40 carbons long, something like that. That sounds hard. And so we don't do it that way. We instead build an ordered thing, a regular array of chains that are straight, like trees in an orchard. Okay, so they're all growing straight up, and they're all in a regular square array. And maybe it's a double-decker orchard, or maybe not. Maybe we put a second layer on top. And we leave plenty of room in there. And we put those things in there, and we know that the molecules are not going to be on top of each other because we build them that way. Okay. And then we let the simulation make the melt for us by turning on the simulation and slowly shrinking the box. Like that. And that works great. And you can use, tools to sort of verify that that your molecules are random enough and have moved around enough inside the box so that they don't remember anymore the crazy regular array that you built them in. And how big, how do you know how big a box to make at the end? Well, you calculate it, because you know roughly what the density of the material was that you were trying to make a melt of, and you know how many molecules you put in, so you can figure out how big the box is that you ought to build. And then once you get that box shrunk down, maybe you'll turn on a pressure control and allow it to adjust the density so that the simulation is, at an equilibrated pressure. In other words, so that the simulation potential gets to choose what it thinks the density should be, which maybe won't exactly be quite what nature knows that the density is supposed to be. So that's a common technique that we use for building a disordered liquid of long molecules that would be hard to create by random insertion. And in a little while, I'll tell you about sort of related techniques that we use to build self-assembled structures. But before we do that, I will describe the Deckhane melt example, which will be our last example that you'll have the opportunity to do. So this builds on, pardon the pun, the experience that you had last time. If you saw the email that was sent and you looked in your folder, you'll realize that your Deckhane folder is gone. And that's because there were some mistakes in it. And so a new tarball, Deckhane.tar, has been created and put in the top level, the short course folder right next to the examples.tar. And so if you haven't already done this, at a certain point, we'll take a moment and you can copy that into your own directory and unpack it. And it, like before, it has a start folder, a ready to run folder, and a completed folder. And what we want to focus on here, we're not actually going to run this thing. What we want to focus on is the job of building the thing, just to sort of see what it looks like. And there's a question. Yes, Margaret's trying to give me a hint about how I can get a pointer. The problem is that my mouse won't go over onto the screen, which is in slideshow mode. So it thinks it's on a projector screen, and that's what's being shared with you, and my mouse won't go there anymore. So I can point with my finger. That's all I can do. Anyway, it's not, it doesn't matter. Okay, so so here's the rough outline of what one does to build this melt. We're going to use that little script buildchain.sh to make a Deckhane PDB file by stacking up those monomers. And you could see it's a short little script, and so it's not, you know, that's an instance of an example of the kind of automation that, you know, that's very convenient to do in a Unix environment for putting together these tools to do a bigger job. So its inputs are the size of the box of the chain it's supposed to make, and those are then going to be stacked up into this orchard structure in a second step. And so I've decided to give the base of each tree a 4 angstrom by 4 angstrom space, and then to make the thing 4 nanometers tall, which is, you know, way plenty of room above every tree. And it takes its input from a little file which just says which monomers it's supposed to put in which order. So it's PEB, PEM, 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 PET for terminus. And that will make this chain called new chain.pdb. And then you can use PDB to GMX to make a top file for that, deckhane.top, which needs to be edited just like the one for the protein, to strip off the header stuff before the part where it says, you know, molecule type, and to change the name of the molecule to be Deckhane, and to strip off the last few lines likewise to make a molecule ITP file. And then we build this orchard, right, with a tool called genconf, and it basically stacks up these boxes, and you can see the option that says, so -f, that's the input file that's being stacked up, okay. -n box is saying 10 boxes by 10 boxes in the plane and 1 box tall. And for technical reasons, it's helpful to tell the thing how many atoms is in this molecule, and then the output is a system grow file, which has got all of the trees in the orchard in their starting points. And then we need to make an MDP file to do this resizing, okay? Because this simulation is actually going to make the box get a little smaller and a little smaller and a little smaller as you go along. Roughly like, presumably everybody here has seen Star Wars Episode 4, A New Hope, i.e. the first Star Wars movie, right? Everybody's seen that? Yes? Okay, remember the part where they're in the garbage disposal thing, and the walls are coming in, and they're, so like that, okay? That's what is supposed to be happening during this resize. And you want to do it slow enough that the molecules have a chance to shake around and move around and fill in all the space as the box gets smaller. So that's an additional option in the options in the MD parameter file, and it's this thing copied down there at the bottom, which is deform equals, and those are the speeds in nanometers per picosecond that the walls are closing in. And you know, and you calculate what that is, and in this case, it's calculated to give the right final dimension in a nanosecond, which is, you know, enough time for the molecules to shake around. So we commonly generate these MDP files by stealing from ourselves, as I think I mentioned when I talked about it. I mean, they're full of parameters, so how do you know what to choose? And the answer is, well, you know, you tend to borrow something that works and change it a little. And so that's what we're going to do here. We're going to borrow from the nvt.mdp for lysozyme, which you have a copy of, and and you can make the following changes. Or I think actually I probably just put this resize.mdp in the start folder if you want to see what it looks like. But this is, you know, just to indicate the kind of thing you do. Here we change the time step because we're not going to constrain all the bond lengths, so we can't quite run as fast. So we change it to a femtosecond from 2. We got to run more steps because it's going to go a nanosecond, so we increase that. And then to keep our output files from getting enormous, we don't save position information or log information quite as often. You typically want kind of 100 frames in your movie and 100 reports in your log file, no matter how long your run is. So that's what we do. And then we add this deform option. So here's a sort of before and after comparison of the lysozyme nvt.mdp file, and then the changes made highlighted in red to the resize.mdp file, right? So and you see the point. I mean, I think I mentioned this before. This file is totally free form. You can put these options in any order. You know, don't group them in some sensible way and stick to it, so that you can just glance at the file and see, oh yeah, you know, I see that they're in there, because there's a lot of these options and it's easy to mess it up. And to be able to look at the file and say, yep, okay, that's just like the other one except this, is very helpful. And you can see that there's comments in here. The semicolon's a comment character, and so you can remind yourself what all the things do with comments, right? So that's kind of how we do that. So then to run this job, well, you need to build yourself a little system topology file, okay, which is very simple in this case because there's just 100 Deckhane molecules in there. So you read in the OPLS force field, you read in the Deckhane ITP file, the molecule input topology file. You give the system a name and you tell it there's 100 Deckhanes in there, and that's what you need. And then, as always with these simulation runs, you do a pre-processing with Gromp that builds a topology run file, and then you run the job, which here you actually to submit it. This one takes quite a few minutes to run, so I mean, I wouldn't necessarily suggest this. You submit it with qsub and away you go. And that resize.sh is a very similar script to the previous job script that we looked at. So that's how we build this thing, and when you're done, you'll be able to see, that the most importantly, that the box gets smaller and the molecules get random, and the energy comes screaming up as the things come together, and the pressure comes down, and the temperature settles down to 300, and things are okay if the temperature has settled down and the pressure has settled down, and also if the molecules have had a chance to move around kind of their own size. Those sorts of judgments are what you use to tell that you've got a decently equilibrated starting point for a melt. So with that, let's go over here and look at the desktop. So if you haven't yet, come on. Okay, so there's Deckhane.tar. at the same level as all the student folders. If you haven't already copied that into your examples folder, do so and unpack it. Some of you have.
So which force field do we choose for this?
Hang on just a minute until I give people enough chance to copy this in if they're going to do this. I mean, you don't have to, you know, this is not graded, right? So if you don't want to do this, it's fine. But if you do, I want to give people a chance to get this thing copied in there. Okay, well, all right. So when you get that thing unpacked, whoop, there's chats coming up here. What do they say? Oh, my on the ball TA say, hey, you know, they might have done the tarball and already deleted the tarball. And yeah, okay, so good. I should stop spying on people's folders. Yeah, so let's see. Whoops. Okay, so here I am in the start folder, and so the first thing we're supposed to do is use this build chain script. And I just want to show you that the MonList.txt isn't anything very complicated. It is literally just a list of the monomers that you want to stack together. And so, you know, this is limited only by your ability to build monomers that stack together. So if I say slash dot build chain dot sh 0.4, 0.44, input from monlist dot text, and after a little moment, wow. After a little moment,
This took me like a second though.
It should have. It took you just a second. Is that what you're saying?
Yeah.
Yeah. Well, you know, time sharing.
Your desktop background looks weird too. When that's happened to me, sometimes it means that it's just like terminal has encountered an error and I have to reload the entire session.
I am just hoping to wait it out. Every once in a while, you remember when I first launched this terminal, it was, see, just be patient, be patient. Okay, so now I have my new chain, right? And then if I make the topology file, it's gmx pdb to gmx, whoops, pdb to gmx -f, because this is the input file, new chain.pdb, -o for the output file, Deckhane.grow, -p, Deckhane.top. And then it asks me, you know, which of these gazillion different potentials do I want? And the answer is, I believe, 15, the OPLS. Fingers crossed. I don't want a water model. Everything looks good. Let's look at Deckhane.top because I want to pull some stuff out of that file. Okay, good. So the very top of the thing, it's set up to be a standalone topology file, which I don't really want. So I don't read in this, and I change this name to Deckhane. And then I go down to the bottom and take out the thing that would define the system, like so. And then I change the name of this to Deckhane.itp, like so. And that's this much of the instructions. And then the next parts are using genconf to build the stack of the box, and then you want to create this MDP file by modifying the NVT. So I'm going to put people in breakout session here, and you can do these things, getting up to the point of gromping the thing. Let's not run it, but let's just gromp it for practice. Hi, everybody. So I brought you back into the main session so that we can go ahead and for example, look at the movie of the completed resize run, which takes about an hour to actually do on 2 processors, so a little bit longer than we want to wait for, you know, actually submitting the thing. So if you go over into the completed folder, you can see my screen now, and you can see I'm in the completed folder in the Deckhane job. That's got everything that comes from a successful run. And so if you type in there vmd resize.grow, what? That's not what I wanted to see. You mean it can't open this display?
Yeah, that's what I'm talking about. Usually when my background of the session looks like that, it's had some problem connecting to the terminal, like the display X window terminal.
Okay, thank you, Ben. I will exit that terminal and make it try again. Is that going to be?
You might have to start the whole.
Oh no!
Session again. Yeah. Maybe.
That's not what
I think you just have to refresh the tab. I don't think you have to like disconnect and kill your job and wait for the job to start again. I think it's just sometimes the internet tab for the web browser doesn't connect.
So you think if I refresh the tab like that?
I'm hoping.
Okay, fingers crossed. No.
Oh no.
Okay, what if I go back to my interactive sessions and relaunch it? Will it know that it's there? My interactive sessions. Yes, maybe. You guys are good. All right, let's see. Doesn't look a very pretty color though. I'm worried.
Yeah, that's what I'm saying. Like, I don't think it's not even going to launch terminal now.
Yeah,
This is like
yeah.
It's not
Okay,
a good
fine.
color.
Then I can't do it, but you can. So
I
what you
can
want
do
to do is go in that folder and I mean, I'm not sure how fast that movie's going to run if I were to successfully share it over Zoom. But what we want to do at this point is have a look at that thing. And so Margaret, do you want to try doing that? I mean, if I make you
Yeah, I'm
you share
trying to.
screen here temporarily, and
I'm
we'll
trying
see.
to get to the right folder.
Yeah, it's you know, Deckhane completed.
I just need to.
Well, while you're doing that, I'm going to
I
kill
just
this,
opened this.
and start a new one, so we can have a little race. We'll see who's.
You can hear. So. Okay, and it should be in the incompleted.
Okay, so I'll stop sharing, and you can share when you're ready.
Okay, not sure. I can start sharing my desktop. So I need to type.
So VMD space resize.grow is how you get started.
Okay.
And that gets you that. And then you want to change the display to orthographic, and change the representation to van der Waals. Not colors, but representations. Drawing method VDW. And okay, and then you can, yeah, it's fine to have them full size, whatever. And close that little window. And one other little fill up you might want to do is you go back to the terminal window where the VMD prompt is, not that, there, and type PBC space box, so you can see the little blue box, because that box will shrink. And now click back over in the window with the molecule. Sorry, I meant the list of the molecules. There. Highlight the molecule. Just there. Now file, load data into molecule, like that. Yeah. And browse your way to the TRR file for resize.
Which file?
Scroll down a little bit at resize.trr. There you go.
This one.
Yep. And then load all at once, and load, and right.
Good.
So now if you close that little file browser window and press play, which is the lower right button on that window you're on.
I never use this one.
The play
Where's
button.
The little.
Oh, this
like
one. This one. Okay.
Yeah, that one.
I did use one.
Yeah, there you go. Now you're going backwards.
Okay.
Backwards is good.
Okay, let's go.
Yeah.
Okay, now it's good.
Right. You see how it's the very first frame was the orchard, right? That was all the straight chains. And well, the very first frame weirdly is the last frame, but the first frame is after that is the orchard. And then the orchard gradually, quickly randomizes itself. And the box shrinks just like in Star Wars, until you get a melt, like so.
Speed it up.
So that's that is a technique that we commonly use Yeah, you see, very good. Turning it around and you see there's space in
The
it.
holes. Yeah.
But exactly, but by the time it's done, then there's no more voids. Yeah.
Yeah.
Great, thank you, Margaret. That's perfect.
Sure. Stop sharing.
Yeah, yeah. Okay, so so let's see, what's next? Oh, goodness. Now I'm seeing the spinning beach ball of death on my presentation. That can't be good. Oh, there we go. All right. Okay, so moving on. I want to talk about another example of assembly techniques to make a non-trivial structure, and this actually comes from the work of one of my students, indeed Ritvik Kali, who's been helping with the breakout rooms. So why is this not advancing? There. Okay, so here is a molecule that's synthetic, but is meant to mimic a biological pore molecule in a lipid membrane, and it's under development as a water purification membrane, but more robust than its biological equivalent, because this thing is not a folded protein. It's a covalently bonded molecule, and you see it consists of a tube, a collar, which is pentagonal, and then two sets of 5 petals that come off of each side, each of which terminate in something with carboxylic acid groups, so that the ends of the tunnel are charged. And it's just about big enough to pass a water molecule, and these have been synthesized and studied, embedded not in lipid membranes, but in membranes made from diblock copolymers, where the blue polymer, as the color implies, is hydrophilic. It's polyethylene oxide of a short oligomer, and the red portion is hydrophobic, is a hydrocarbon. And so the challenge is to prepare a self-assembled bilayer of this stuff with a pore in the middle in a realistic arrangement. And of course, that self-assembled monolayer is self-assembled bilayer is not an isotropic structure. It has a normal and so on, and it's planar. But it's also not a crystal. It's the chains are quite disordered and so very tricky to build. And so the technique that we've used to build this thing is roughly like the orchard technique that you saw. You build an orchard of these surfactants, in effect, with a space in the middle for the pore molecule, like a fountain in the middle of the Tuileries or something, and then you have an upside down version of it below, in order to make the other side of the bilayer. And then by degrees you equilibrate this thing, first energy minimizing it, which tends to make the molecules clump together, with the pore frozen so as not to mess up the shape of its petals. And then you gradually simulate this thing and add water and so forth, to approach from this idealized structure to this self-assembled structure here. So we're looking at it now rotated 90 degrees, in various views prepared artfully by Ritwik. You can see the pore molecule here. Here he's highlighted a couple of the hydrocarbon chains, but not all of them, so that you can see that they're largely normal to the interface, but not totally, not rigidly all trans or anything. The blue here are the hydrophilic parts of the polymer, and this is water outside. And those hydrophilic parts tending to lie down rather flat and in a disordered way on the surface of this bilayer. Most importantly, there's a narrow thread of water that goes right through the pore, and we didn't put that there. That equilibrated its way into the pore. So, so what we're interested in, and what Ritwik has been quite productively studying, is to examine both the structure of this thing and how it depends on the particular choice you make about, for example, the dimensions of the copolymer chains, because you could, how thick do you want to make the hydrophobic and hydrophilic region? Well, I mean, you want to make it so that the pore molecule is happy in there, so that it has a compatible dimension in order to in which to sit. But most importantly, you want water to freely pass through this pore. And so so what he's been doing, just to give a tiny little taste, is to both measure things like the profiles, density profiles of the different components to get a sense of the structure of this thing, and that is done using the very similar approach that was indicated yesterday of looking at the density profile of a water membrane, a water slab. Okay, but now we have a multi-component system, and so we can look at the density of the different pieces. And to study the mobility of the water, to study how easily it could pass from one side of the pore to the other, one approach is to simply sit and watch it diffuse. And so you identify those water molecules at the beginning of a short simulation, which are actually in the pore close to the collar, and then you watch their mean square displacement as a function of time. Now, that's a quantity that fluctuates in time, and so sometimes the molecules move readily and sometimes not so much. And so the top graph there is multiple runs, watching the same, watching a few water molecules in the pore as they diffuse back and forth and looking at their mean square displacement. And so one wants to average over a lot of such runs in order to get a measure of the average mobility of the water in the pore. And the mobility of the water in the pore is then going to be intimately related to how easy it is to push water through the pore with a hydrostatic pressure difference, as one needs in osmotic, in reverse osmosis, right, where you're pushing water through and not letting the ions go through, because basically they and their solvation shells don't fit in that little hole. And so changing the design, it turns out, makes quite a big difference in how readily water diffuses in that pore. And this is only the beginning of the story, but just an indication of the kind of thing that you can do with simulations and mildly clever self-assembly techniques, as well as techniques for measuring quantities on the nano scale. So so that's an example of a real life, if you want, or a real research life example of the kind of things that we use these simulation techniques for. And I would say, notice the size of the system. That is a full view of the simulation system. It's got I can't remember, but maybe 50,000 atoms, maybe a little bit more, somewhere between 50 and 100,000, something like that. And these simulations run on, 8 or 16 processors or so, depending on, how greedy one wants to be, and take quite a while, particularly when you are averaging over multiple runs, to acquire data that's meaningful over multiple systems is many weeks of computer time. But this is sort of a scale at which we commonly work. Right. So so the next topic I want to touch on which we've really only seen one little example of, is simulations in which we don't simply watch things move around, but we actually apply certain kinds of external forces. And there are a lot of capabilities in GROMACS for that purpose, and a lot of uses that that kind of thing has. So, so that the name for that kind of technique is in general called pulling, for historical reasons, because one is applying some force and pulling on some biomolecule to see what it does. And a couple of examples of what you can do with it. Well, we saw one already in the electrophoresis case, where there what we're applying is actually an external electric field, making the two kinds of ions drift in opposite directions and observing the slight drift of water that results. Another kind of example of this would be to calculate what's called the potential of mean force. So for example, if you had a micelle, okay, which is a self-assembled ball of surfactants, a spherical micelle in water, the hydrocarbon tails point in and the ions are on the outside, sort of like, I don't know, like cloves in a round ham, cloves in a physicist's ham, right? Which would of course be round, like all physicist objects are round. And so if you can tell how tightly held the surfactant is in the micelle by pulling it out to various distances and measuring the average force needed to hold it at different distances from the center. And if you do that slowly and carefully enough, you can figure out the work required to drag it to any given distance, and that work is the integral of the potential of mean force, or conversely, the derivative of that work is the force that you're measuring. A third example, which I'll tell you about, again, work from our group, is to use external forces to learn about the osmotic pressure of ion solutions. So I'll tell you about a couple different ways of studying that question. One of which is to confine ions between sheets and to measure the force on the sheets doing the confining. And these sheets are things that could only exist in a simulation, because we can make, for example, graphene-like sheets that are invisible to water but repulsive to ions. And so they do a perfect job of confining things. And furthermore, we wrap them around the periodic boundary so that they are under tension and nice and flat. And so what I'm talking about looks like this. Here is a collection of sodium and chlorine ions trapped between two sheets, which, as I say, are invisible to water, but interact repulsively with the ions. And they are connected across the XY periodic boundary, so they're continuous across, and built in such a way that they're under tension so that they stay quite flat. And the ions are pushing against those, right? The osmotic pressure of that ionic solution is basically the same thing as the pressure of a gas or liquid of the ions. They would like to have more room to run around in, so to speak. Their entropy would be larger if they had more space, and so they exert forces on these membranes. And if you then constrain the membranes using these pulling forces, trying to hold them at a certain spot, then you can measure the force required to hold them at that given spot. And that force will fluctuate wildly in time as more or fewer ions make force on those membranes. But if you time average those forces, you can measure the net, the average force outward on each of the membranes, and therefore determine the osmotic pressure of the solution inside. And that works well, but not so well, because for one thing, those sheets impart a lot of structure to what should have been a uniform solution of ions. Because there's a hard flat wall there, there's a tendency of the ions to sit right up against the wall. And so if you look at the concentration profile of the sodium and chlorine ions, which are what's plotted there, and I can't remember which one is which, but if you look at the picture, you can probably figure out, let's see, the blue ones are the sodiums and the cyan ones are the chlorines, and the blue ones are especially structured, I think. That's the ones with the big tall peaks. Anyway, this is bad, okay, because in simulations, walls are our enemies unless we want to study walls. Periodic boundary conditions is our friend because it allows us to study small regions of liquid without any walls. And so this is a somewhat fraught way of measuring osmotic pressure, with the additional problem that if you want to measure an osmotic equation of state, you've got to vary the number of ions in between those sheets, or equivalently vary the distance between the sheets. And so, you know, to get a whole osmotic pressure curve requires like a whole series of simulations. So we thought of something better. And that is to confine the ions with a harmonic potential and no walls. So, so here's a snapshot from a small version of such a simulation in which there's a harmonic potential in the horizontal direction. Okay, and so it's minimum in the middle of the system and larger near the outside. Like the green curve in the upper left graph there, where we're looking at half of the system, right? The other side would look just the same. And in such a potential, in equilibrium, ions that weren't interacting with each other very much, in other words, were behaving as an ideal gas, would give a Gaussian distribution, right? Because their equilibrium probability distribution would just be e to the minus beta u, where u is this harmonic potential. If those ions were not quite ideal, for example, if they resisted being concentrated beyond a certain point, then you might expect that if you tried to concentrate them more, that what was a Gaussian would tend to be a little bit flat-topped, right? Because the concentration would resist getting high in the middle. On the other hand, if the ions were maybe a little bit attractive to each other and prone to condensing, then maybe it would tend to glump up in the middle, even more than a Gaussian as the concentration got high. So how can you actually use this to measure the osmotic equation of state? Well, imagine a slice of the concentration profile indicated in red, a slab, if you want, of the ions. And imagine think about the balance of forces on that slab. And to make that thinking a little easier, insert a little, you go to the physicist's store where you get massless ropes and frictionless pulleys and things like that, and you get a little thin membrane, invisible to water, that can notionally confine these ions, okay? And those membranes feel an osmotic force from the ions in the slab, and they also feel an osmotic force from the ions on the other side. And the membrane is, you know, one of your standard massless membranes. And so it's in equilibrium when the system's in equilibrium. And so the set of forces on these membranes must balance, and they are three, okay? There's the pressure on the left, where the concentration is a little higher, and the pressure on the right, where the concentration is a little lower, and the force from the confining potential. The three of those have to sum to zero for each slab. And that, if you take the sort of differential limit, leads to the differential equation at the upper right, where the osmotic pressure, pi, is obeying a differential equation, which, because we know u and can measure phi, we can actually integrate to get pi. And to do this, what we have to do is put every single ion, plus and minus, in a harmonic potential that tends to confine it to the middle of the system with about a 4 kT energy difference from the outside to the inside in order to prepare a decently tall bump in the concentration profile. And then, you know, average for a right smart time to measure a quite nice concentration profile. And to do that, we use these pulling options in the simulation and generate with a little script, you know, because there's lots of lines. There's a line, you know, there's a block of those pulling options for every single ion in there. So we have to generate those with a little script. Kartik, you have a question.
How dependent is this value to the harmonic potential you impose on it?
That's a good question, and I'll give a little bit of an indication about that in the next slide, I think.
Okay.
So as I say, we chose a harmonic potential that confined things by about 4 kT from the outside to the inside. And one of the things we did as a check of whether we were seeing artifacts in the resulting concentration profile was to do it in twice as big a box. So now all the system dimensions are twice as big. The potential, therefore, is not as sharply curved, right, by a factor of 2. It's still 4 kT from the outside to the inside, but it's not the same harmonic potential, okay? But if you plot the concentration profile in appropriately scaled distance, it looks exactly the same, the red versus the blue. When we made the system, you know, twice as big in every dimension, we put 8 times as many ions in it in order that, you know, the system would effectively be the same. And it is, which is saying that, you know, that it doesn't exactly matter, you know, what the detailed shape of this potential is, but only the, you know, sort of scale of energy difference from out to in. So why are we doing this? Well, it's because in many circumstances in real experimental systems, ions get quite concentrated. For example, condensing around the surface of a charged colloidal particle, or in the vicinity of an electrochemical surface, you know, a platinum electrode with voltage on it in a strong electrolyte is going to gather countercharges in a very short distance of a few nanometers. The double layer, you know, in the vicinity of a platinum electrode is basically a multimolar salt solution. I mean, of predominantly one ion. And so if you want to be able to simulate things like that and be realistic about it, then you need to be sure that that your interactions between the ions and the water and stuff under those strong concentrations are reasonable. And you remember how OPLS was called that because it's, you know, it's the optimized potential for liquid simulations, and what they did was to adjust the interactions in such a way that they got sensible liquid behavior, sensible densities, sensible, you know, boiling points and things like that. Basically, sensible equations of state for the liquids. Well, what about ions? You know, you want to simulate chlorine and sodium in water, but you're not interested in salt crystals. You're interested in the sodium and chlorine in water. Okay, so basically what you want to get right is the osmotic equation of state, and maybe at quite high concentrations. So how we do? Well, the stock potentials turn out to be not so good. And you know, that's not surprising because, I mean, to adjust this turns out to be a little bit delicate. If you use the stock potentials, the osmotic pressure undershoots the measured osmotic pressure, which is, you know, well measured and tabulated, especially at concentrations above a molar. And what's happening basically is that the ions are just a little bit too attractive for each other. And so they're tending to cluster. And if they cluster, then they are not running around as independently and therefore don't make as much osmotic pressure. Okay, well, so if you want to adjust that, you make the ions ever so slightly more repulsive for each other in terms of their short range repulsion so that they can't cluster as much. The sodiums and the chlorines can't get quite as close. And as a result, then we can make the simulated and measured osmotic pressures basically coincident. making a few percent adjustment in basically the size of the ions that governs their mutual interaction. So we tune the potential, in other words, to get the right answer, but would hope that under other circumstances where ions would be concentrated, that they would behave sensibly. And so that's the kind of thing that one has to think about sometimes in terms of validating simulations. So that's another example of work from our group that connects with what we're talking about this evening. So so the last topic that I want to talk about is how to run faster. And what everybody wants to do when they're simulating is make their simulation go faster. So what are some of the ways that that's done? So the first thing is that MD simulations are parallelized, right? And they're well suited to parallel execution, that is simultaneous execution on multiple processors. And how that's accomplished is by what's called domain decomposition. So you take the whole simulation system and break up the spatial region into some boxes, and each of those domains is being handled, or the particles in each of those domains is being handled by one CPU. And of course, they have to talk to each other across the boundaries. Particle coming your way, particle just over here that you should be interacting with. So they're passing messages to each other, and so one has to think a little bit, and the people who design simulation software like this have to think a lot about machine architecture, right? So modern cluster computers consist of multiple nodes. Each of them have typically two chips in them, each of which have got multiple CPUs on them. So for example, the basic nodes on Penn State's cluster have 2 CPUs with 10 cores or processors each, and those share memory and have very fast communication within the single chip and motherboard. And so and more recent incarnations of nodes have as many as 32 or so processors, 2 times 16 or something like that. And so if your job fits within a single node, then you don't need any internode fast communications. If you want to run something bigger than that, then there are fast interconnects between something called InfiniBand, which is a very fast and rather expensive interconnect between different nodes, which will allow you to run jobs on multiple nodes essentially as efficiently as you could do it on a single node, but it's somewhat expensive. And so you can speed your jobs up then by throwing more processors at them to a point. So eventually, if you keep doing that, then the region of space, as it were, that each processor is handling doesn't really have enough particles in them, and they spend all their time talking to each other, and so so one of the things that you do when you're trying to make estimates about the how well your job is going to run and so forth is you do timing studies. And so you can run a small job on a few cores in order to find out how a bigger job on more cores will run. And the scaling is more or less linear. That is, if you take a job with 50,000 atoms and you run it on 4 cores and you increase the system size by the cube root of 2, and then you have 100,000 atoms. You run it on 8 cores it'll basically run at the same speed in nanoseconds per day. So if you're in a simulation group, your advisor is constantly bugging you because he can't remember. So how many cores you're running on and how many nanoseconds per day are you getting? And, you know, and that's what you need to know in order to plan your runs, right? In order to know how long the run will take. It's like, again, you have your results by next week or next month, and what are we talking about? 3 dimensions is a demanding place to be, right? Because, you know, you increase your system dimension by a factor of 2, which doesn't sound like that much, and all of a sudden you got 8 times as many particles. So we have to be very conservative about choosing system sizes, especially, you know, to avoid simulating empty water, for example. If you think about Ritvik's pore simulation, you know, there's the pore and there's the membrane and there's a certain amount of water on either side, and you want to be kind of stingy about, you know, I need to have some extra water so that my membrane doesn't see itself through the periodic boundary. I need to have some extra membrane so my pore doesn't see itself through the periodic boundary, but not much. You know, let's try to be cheap about that. So those are issues that one thinks about a lot. A rough rule of thumb about how greedy you can be in terms of throwing cores at the job to make it run faster is you don't really want to go below about 1,000 atoms per core, because then the system starts talking to itself. The processors start talking to themselves too much. And you can see that in the log file. If you look in the log file, that the bottom part where it's reporting about how much time it's spent doing stuff, there's some lines in there about inter-process communication. And if those start to get sizable, it means you didn't have enough atoms per core. So that's some of the thinking that goes into you know, sizing the jobs. Right. So a more recent, but not so recent development now in hardware for simulations that's made quite a difference for molecular dynamics are graphical processing units, GPUs, and these are not, how should I put it? They don't give you factors of like 100 or something in speed up. In practice for atomistic MD, they can speed things up by factors of 2, 3, 4, something like that. And what they're for, because they're basically big parallel processing chips that can do, you know, many strictly parallel operations simultaneously, and they've given us a way to break out of the failure of Moore's law. You know, for a long time, processors were getting, you know, smaller and smaller and faster, and then, you know, we got to a place where the wavelength of the shortest wavelength of radiation that we can use to etch chips is, I mean, it's just as small as it's going to get, and so chips aren't really getting length scales any smaller, and the direction that things have gone have been these, you know, special purpose parallel processing units. So they're very good for doing the same thing over and over, as, you know, as for video processing, where you're dealing with all the pixels in some movie, and that's been adapted for computing things like the non-bonded interactions that are the thing that take all the time in computing the force. So Leonard-Jones, they are not good at present. People have not figured out good ways of computing the Coulomb interaction using these things, at least as far as I know. And so there's a certain amount of balancing that has to be done in terms of making sure that the ratio of CPUs to GPU, and that's the way it works. You typically need multiple CPUs to keep one GPU busy. What that ratio should be and how to vary it. There's 2 different senses in which one can ask that question. One is you're buying hardware and you want to know, okay, my nodes are going to have, you know, 32 cores. How many GPU units should I have? You know, is 1 enough? Do I need 2? You know, what's the CPU to GPU ratio? And so one does a cost benefit type study, because GPUs are expensive. And certainly, you know, adding more will make things go faster, but it doesn't necessarily give you the best nanosecond per day per dollar figure. Okay, you know, if you're spending money, you're trying to buy nanoseconds per day, you know, what's the right ratio of CPU to GPU to do that? And it depends somewhat on the application. So for atomistic MD, you know, ratios of CPU to GPU on the order of 8 to 1 turn out to be reasonable, at least for the generation of GPUs that our group's cluster has. And that's not necessarily the right architecture for other kinds of projects, in particular for machine learning or other kinds of things which are just GPU gluttons. If the machine's already bought, okay, then what you really want to do is just worry about balancing the CPUs to GPUs so that everybody stays busy, right? You don't want the CPUs to be waiting on the GPU for its part of the job, and you don't want the GPU to be waiting on the CPU. And so the log file, the output of a GROMACS run with GPUs will have information in it telling you what the duty cycle ratio, I don't remember what they call it, basically the ratio of time spent by one versus the other. And you want that to be around 1, which is basically saying the CPUs aren't waiting on the GPU and vice versa. And if you don't have it like that, you're wasting resources, which is, you know, not good behavior. Right. So so a different sort of question to ask is, you know, given the hardware that you have, what is it that's limiting the time step? Why can't I just take, you know, why can't I take a time step of 2 femtoseconds? Why am I stuck with a time step of 1? What can I do to make the time step a little bigger? Because if I could just take the time step of 2 femtoseconds, I'd have half as many steps, and my nanoseconds per day would be doubled, right? So clearly, I mean, clearly there's some reason why you can't do that. And the reason, again, comes from Star Wars. If you'll remember the jump to light speed, and if you're a little fuzzy on the exact dialogue at this stage, you can read it here, where, you know, wise Ben Kenobi's asking, well, how long before you make the jump to light speed? They're being chased, you know, by Imperial starfighters at this point. And Han says, well, it'll take a few moments to get the coordinates from the Navic computer. And Luke, who's always anxious at this point, are you kidding? At this rate they're gaining? And Han turns to him and dresses him down and says, traveling through hyperspace ain't like dusting crops, boy. You know, because if you don't calculate it right, you'll wind up in the belly of a star. Well, not really, because space is mostly empty. But liquids aren't empty. And so when you have 2 atoms, you know, coming together at a certain speed, okay, you want to rather accurately model that collision. If you take twice as big a time step, then you wind up getting too close together relative to where the turnaround point would have been in that collision. And when you do that, the energy is big, and then the force is big. And then the atoms go flying apart, and then they land in the belly of some other atom, and then their force is big again, and the whole thing goes to pieces. Or equivalently, if you've got 2 bonded atoms, say a carbon and a hydrogen, you need to be able to model this oscillation. And if you take too big a time step, then the hydrogen will get too close to the carbon, and then it goes flying away, and then this spring goes nutty. Those things limit the time step. And so that suggests some things that one might do to boost the time step. I mean, who's really interested in modeling carbon-hydrogen oscillations anyway? Because, I mean, the spring is stiff, the displacements are small. You know, we're not doing spectroscopy here. We're trying to model the motion of molecules and their interactions. So why not just fix the length of the carbon-hydrogen bonds? And then you don't have to follow that oscillation. You just figure out where the hydrogen wants to be at any given time step so that the length of the hydrogen is fixed and the torques on it are, and the torques on that bond are balanced. And that's what the links, which stands for linear constraint solver or something, does when you tell it to constrain the length of hydrogen bonds. And that allows you to boost the time step up by about a factor of 2. And that's real money. If you have molecules that are not long linear chains, you can constrain all the bond lengths if you're not interested in changes of the molecular shape that involve lengthening bonds, which are in general quite stiff and therefore involve very small changes in shape, and that'll get you a little bit more in the time step. Although this does not work well, as I mentioned, when you have long linear molecules, because if you try to solve the constraints of all of these linked bonds all the way down the chain, that just turns out to be a mathematically very awkward problem. Another thing you can do is to just throw away the hydrogens altogether. Maybe you don't even want to see them. I mean, if you're going to simulate Deckhane, why not just represent the CH2 as a little ball? And the CH3 on the end is a little ball. Those are called united atoms, and you can do that with a certain loss of chemical fidelity. Okay, you don't want to do that with molecules that do hydrogen bonding, right? I mean, so if you're going to do hydrogen bonding and you've got water in there and you've got polar moieties that the water wants to stick to, those waters have to be represented as things with hydrogens, right? Not little balls. And the carbonyl or whatever that the thing is bonding to needs to be represented, so that you can see the oxygen and the partial charge on it. But a certain amount of this kind of coarse graining for some kinds of things will allow you to boost the time step still further. And so coarse graining, which is what we're talking about now, requires some decisions about what you're willing to give up. So the top picture, the green, right, is showing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2, 4, 6, 8, 2. Deckhane, coarse grained as united atoms, and that for many purposes that's probably fine, although not for simulating ordered phases of Deckhane, for which the particular shape of where the hydrogen bumps come off the carbons are important. And if you simulate those phases with united atoms, they melt at totally the wrong place, and they have the wrong crystal symmetry and so on. If you want to be still more greedy, you might sort of simulate every 3 carbons as a little ball, and maybe that's okay if what you're trying to do is polymers, but it certainly misses the trans zigzag. So there's decisions, as with any approximation, which this certainly is, about what to do, and what you're giving up by doing it. Which brings me to the last case study, and indeed the last topic of the short course, which is work in progress of Pooja Agarwala, our other TA, has been helping out yesterday and today. And so this has to do with simulating the relatively stiff sorts of chains that are of interest for semiconducting polymers and photovoltaics and so on. So an example of that is poly-3-hexylthiophene, for which this is a repeat unit. And one can simulate this thing, with all the atoms present, and it's a fairly expensive and slow thing to do, because the polymers are quite stiff in the sense that their main chain trajectories are not very flexible, and that's ultimately because the thiophene ring, the arms, the bonds to neighboring thiophenes that come out are almost horizontal. And so even if you rotate around that dihedral, it doesn't swing this chain around a very big cone with respect to that chain. So the trajectories tend to look rather semi-flexible. And that makes the dynamics slow. So you can do united atom and replace the hydrocarbon tails, which are really there just to kind of solubilize these things. You can replace them with united atom groups and maintain all the atoms in the central ring, and that definitely speeds things up. You can replace the moieties, which are these planar thiophene rings with spherical beads, and it's deeply embedded that the beads are going to be spherical because your interactions are all central potentials and they're pairwise, you know, Leonard-Jones type things. So as soon as you replace those rings with one moiety, it's a round moiety, and then your molecule doesn't know anymore, so to speak, that it's made of planar objects, and so it screws up the packing. Doesn't pack the way it would pack if it were really planar thiophene rings, which are quite thin compared to the other dimensions. So that's not good if you're interested in realistic local geometries. So and furthermore, you've lost your dipole, okay, because the dipole came because the sulfur's got a lone pair on it, and that's negative, and the canceling positive charge is elsewhere in that ring, and this thing's got a dipole of 2 dBi or something, and you can't represent that with a featureless sphere. So so one capability that we haven't talked about yet in GROMACS is the ability to define what it calls V-sites, or virtual sites, atoms whose positions are geometrically determined by the positions of other atoms. So in the case of the ring of polyhexylthiophene, these blue atoms there are in this case V-sites, virtual sites, whose positions are geometrically determined by the position of the 3 purple real atoms on that ring. So because this thing is basically a rigid pentagon, we kind of know where the blue atoms are if we know where the purple atoms are, and so we don't have to do separate equations of motion for those blue atoms. And furthermore, we know that that ring's pretty rigid, so we can actually fix the bond lengths between the sulfur and the carbon, and even the distance between the 2 carbons across the ring, again reducing the number of high frequency degrees of freedom and allowing us to take a somewhat larger time step. So whatever you can do to reduce the number of degrees of freedom and whatever you can do to reduce fast vibrating stuff allows you to have fewer equations of motion, which is cheaper, and also a bigger time step. And so here on the right is another such molecule of interest, a more complicated one than polythiophene, an acceptor molecule called, I don't know what it stands for, indeno dithiophene benzothiodiazole rhodanine, something like that. And then the O talks about those solubilizing tails that come off. Anyway, O-IDTBr. And it's made of rigid moieties too, and so only the purple atoms are necessary to specify the orientation of the non-flexible bits. And and then you've got a few dihedral angles between them, and those are the important degrees of freedom. So we represent this thing with very few, relatively speaking, real atoms, with the other ones determined by the position of those real atoms. And the stiffer the thing is, the better it is for us. The fewer atoms you really have to let have their own equations of motion. So the kinds of things that Pooja's been busy doing with this are things like trying to study the properties of the interfacial region where these 2 immiscible materials will nonetheless locally mix in the interface. And so again, we're using this technique of building an idealized structure and then shrinking it and equilibrating it, which you see here. And this runs quite fast and prepares a well-equilibrated blend of oligomers, short molecules of the P3HT, and then these full-sized acceptor molecules. And then what do we want to do with that? Well, we're interested in electronic properties of of the intimate contacts between the two kinds of molecules. So, so we can sample many meaningful geometries of where these two dissimilar molecules come into intimate contact, or as a sort of warm-up exercise, where in just a polythiophene melt, where different chains come into intimate contact. And one of the things that simulations, at least if you keep the molecular shapes, are great at is averaging over those arrangements. That is, giving you a whole set of snapshots that, you know, whatever else you can say about them, give kind of decent orientations and relative locations of different moieties on different chains. So in an electronic properties story, which, you know, is beyond the classical simulation, there's a little bit of electronic overlap between the highest occupied molecular orbitals, the HOMOs, or the lowest unoccupied, the LUMO, of moieties, which allows electronic communication between these chains. And it's very much of interest to know what those are. But then, of course, you need a valid set of snapshots coming from such a simulation in order to evaluate that. So you can extract many such near neighbor pairs in an automated way from such a simulation, and then give those pairs, you know, well, cap them off with hydrogen so that they're, you know, well-defined molecules, because I'm just looking at one monomer on each chain, and then go and compute the electronic overlap by giving this pair to Gaussian and asking about the splitting of the degeneracy between what would have been the two isolated HOMOs of these two molecules, or two isolated LUMOs, had they been far apart and not electronically interacting. As you bring them together, those two modes, the two HOMOs on these two molecules, hybridize a little bit. You get a little bit of a bonding mode, which is a little lower in energy, where the electron's shared between the two, and a LUMO, which is a little bit anti-bonding with a node in the middle. And the splitting between those is telling you about the degree of electronic interaction between them. And so we see not one such splitting, but many, depending on the details of the nearby arrangements. And there are a minority of rather large couplings here, you know, large in the sense of a few hundred millivolts, which is, you know, a relevant energy scale for, you know, significant electronic coupling between the chains, which allows, in the end, free carriers to move around in the melt. So that's work in progress, very much so, but gives, again, an idea about how one can use mildly clever methods for accelerating simulations without giving up the faithful representation of the molecular shapes and interactions. Okay, and with that, I will stop and take any questions that people have. I believe we also have, before you go away, I don't want it to let anybody leave, but we have a pair of polls to do, which are sort of an exit survey of your, they're anonymous, by the way, just to let you know, of your evaluation of the short course. But before we get to that, I'll take questions that people have.
I have a question that I might have missed. In this, you're extracting two pairs, as in just a pair of molecules, right? So you are not considering the effect of its neighbors?
That's right, because the thing that we're calculating, I'm sorry I had to shut down the share in order to get my mouse back, actually, but I can put the share back up if I need to. Yeah, the thing that we're doing is extracting two monomers and asking about the electronic coupling local to that pair of monomers. That's not, you know, the entire solution to what would happen if you had two chains together, but it's an ingredient in a separate kind of electronic calculation of that. Yeah.
Okay, thanks.
So my understanding of how the forces and everything are calculated is that that's kind of like the bread and butter of the code. And so that's handled automatically. So this blocking that you do when you treat, for example, one carbon and a couple hydrogens attached to it as a single thing, that's not done by is that done by replacing them with an effective object which you then
At the
created other potentials for, or by setting constraints?
It's so going to, for example, united atoms, what one does is then your configuration tells the positions of united atoms, and your topology file tells about the bonding of united atoms, and the interactions that you specify must be for united atoms. So so you've gone off of the OPLS potential at that point, and you specify your own potential. And so it's a significant amount of work to do that. But it's worth it in terms of speed up.
Right. So so you do create
go all the way back to the beginning. Right.
Yeah.
Because otherwise, otherwise you wouldn't be reducing the number of degrees of freedom.
Right. But there is also a way, so you don't have to create a new fictitious atom, but because you can unite them, but you do still have to make the potential. So not too different.
I mean, you basically do have to create a new fictitious atom, and know what its properties are, and know what its bonding to its fictitious neighbor are, and know what its what its Lennard-Jones coefficients are and its partial charges. You have to start over again as if the united atom were the atom.
Okay, so it is in fact all the way from the ground up.
All the way back.
All right, thank you.
And there are united atom potentials that have been developed by by various groups. One of which is called the TRAP potential. I forget what that stands for, but developed by Ilya Ziepman at Minnesota, his group, and they've worked through a lot of different molecules, determining united atom potentials appropriate to different kinds of local atom regions, just like OPLS, only no hydrogens.
Thank you.
Other questions?
I suppose this is a slightly different sort of question.
Sure.
But what would you say you find most frustrating about using GROMACS or doing this sort of modeling? Are there things that you wish the software did that it doesn't do, or a specific task that's always?
Well, I've tried to indicate those things as we've gone along. I mean, and I have maybe not thought as creatively as one might about how those things could be rectified. Definitely the building of topology files and the defining of potentials for new situations is always a fair amount of work. And we have in-house developed various workarounds and helps to that, but not like a grand solution. We could talk about that more offline, but that I think is broadly appreciated within the community of simulators as being just a hard job that people haven't necessarily figured out, some automated way to deal with. Yeah, and it makes it a little bit difficult, for example, to quickly change what molecule you're simulating within a family of molecules. And synthetic people with their armies of synthetic grad students and postdocs, I mean, could just totally overwhelm you with, well, what about this molecule? And they got the molecule of the week, which is different from that one. And every time they do that, I mean, it's like, oh my God, am I really, going to invest the time in working up potentials for that one? So we have been, and indeed this V-side approach for a family of these semiconducting stiff molecules has with it some additional techniques that I don't have time to talk about for trying to simplify the job of preparing topology files for these things. And we don't use PDB to GMX for that. So. Other questions?
Potentially related to the last question about like what's troublesome in GROMACS. You listed some things that were the great points that really made GROMACS your MD program of choice.
Yeah.
So what other ones had you considered but ultimately not chosen for, and for what reasons?
LAMPS certainly was a finalist, if you like, and has many virtues. It has an active development community. It's open source. It's got a broad suite of capabilities. This is going to sound silly, but what made the difference was the documentation. Because I was like a neophyte in this, and I really needed to be able to read something that I understood what the heck it was doing, and that makes a huge difference. And if you go and spend time reading the GROMACS manual, I mean, you really understand how the thing works and what it's doing. That was time well spent on their part.
I will say that LAMP's documentation has improved, at least presumably since 90.
I'm sure it has. I'm sure it has.
It's much better now. Although I will say, so I work a lot with LAMPs. GROMACS, looking at what you do, seems perfectly suited for what you do. It has a lot of utilities that you can't find in LAMPs, especially working with residues, especially since you're working with molecules that naturally decompose to those. I work with things like graphene, which does not necessarily decompose to a residue, especially if you're making defective structures. And so,
right, that's right, and so it's well suited for organic molecules.
yeah. Whereas
not because of the forces or interactions, but because of the difficulty of preparing topology files for those things.
Yeah. Whereas in LAMPs, I mostly just LAMPs works just off of particle positions, which sometimes is better. Sometimes it's much better to do things the way GROMACS does.
Yeah. So I mean, its origin was in biomolecules. So.
Right. Like in LAMP, sort of doing I think a lot of the tools you can do where you can just fix specific geometries, fix angles, and fix bonds are a lot harder to do, where they're very native to GROMACS. And so a lot of the analysis you can do for your systems is essentially,
really I mean, although those various conveniences and inconveniences of different platforms do vary, I mean, fundamentally the structure of any simulation platform has to have those elements that I described, and how convenient or inconvenient it is to deliver those is a matter of the time and care that the implementers put into their particular platform. Other ones, I think the NAMD, the one that's produced and developed by the University of Illinois, has a similar provenance, right? Because that's also biomolecules and so forth. And indeed, that's where VMD, the visualization program, comes from. And their whole platform, I think, is a very good one as well. So that's, I just picked one, and it's a huge investment to learn the thing, so you don't readily change it. But mostly we would try to focus on the physics we can do with it. Other questions?
I have something to ask about the umbrella sampling method. So is that method really, is GROMACS useful for calculating the entropy of solvation? using that method? Like for sake, if I calculate the delta G of solvation of a molecule, and then
Yes. Okay. So yeah, you'll notice I never mentioned anything about computing any free energies of anything.
Yes.
Yeah, free energies are hard. Intrinsically so, because essentially because the entropy is not a function of where everything is and how fast it's going, right? The energy, the pressure, the temperature even, all those things are functions that you can write in terms of where everything is and how fast it's going, right? The temperature basically is, measurable by the internal kinetic energy, okay? The potential energy, the pressure, even the instantaneous pressure is a measure, can be measured by the forces between stuff right at this moment. But the entropy is not like that. And in general, the way that you get entropies and free energy like quantities is you need to integrate with respect to something. And so I didn't discuss this, but for example, if you want to measure Henry constants in simulations, like how much does this solute want to be or not want to be in water versus vacuum? You can think of two ways of doing that. One would be if you had an interface and here's the liquid and here's the vapor, I'm going to take that molecule and I'm going to hold it here, and I'm going to hold it here, and I'm going to measure the force, and I'm going to hold it here. And it doesn't care up here because it's vacuum and vacuum. When it starts to see the interface, it cares, and it either feels like it wants to go in or it feels like it wants to go out. And so you measure the force profile as you cross this, and you integrate that, and then you get a work. Okay, and that's the work to go in or go out. That's okay, except this interface is kind of ugly. The thing that people actually do is they take the molecule and they make it a ghost. And so they put it in the water, but it doesn't have any interactions. And they slowly turn the interactions on, and then the water starts pointing at the molecule or otherwise changing its energy and its entropy. And there is a way of calculating the thermodynamic work to slowly turn the interactions on. That method and variations of it are something that our group uses a lot. And in, as I've said before, kind of a mildly clever way, a non-standard sort of way. But I didn't, it was a little bit too far afield for this short course to discuss those kinds of things. But that's current, that's sort of state-of-the-art, current cutting-edge stuff, improvements and variations of that kind of method.
Yeah. So I was actually trying something similar, and I did calculate the free energy. So I did calculate the free energy of solvation for molecules, but then I was interested in the entropy change of solvation, like the entropy change.
Right. So you want to divide that solvation free energy into an energy and an entropy.
Yes.
Okay. Well, so if you've calculated, well, right. So the procedure there would be, if you've calculated the free energy, and what you wanted to know was, well, how much of that's entropic? Well, then calculate the energy before and after you make the molecule visible and subtract, right? Because what you calculated by the thermodynamic work was E minus TS, basically. And so if you take off the E part, and that was easy to measure because it's an energy, right? Then you can get the TS part. And that's a very interesting thing to do, for water solvation, because there's going to be some entropy loss, right? Because the water's pointing toward your solute. And how many kb is that, right? How many water molecules gave up how much entropy is kind of a insightful thing to ask. So that's a very good and achievable question. I mean, once you've done the hard work of calculating the free energy of solvation.
Yeah. I like trying that actually made me realize that the much difference is there in the entropic part and all these sort of things. So for that, to minimize the error bar, probably the MD simulation takes like, big system, 100 nanosecond or something like that.
Yeah, you don't need such a big system because those effects are quite local. So there's no point in simulating a lot of empty water if your solute's just here. You want to simulate a rather small system, but you need to simulate it a long time to get good statistics just from the time average. And another thing I didn't talk about in this short course, but it's very important, is how one goes about determining error bars for measured average quantities. And the general story of it is you've got a fluctuating time series, the average of which is the thing you want. And you need to know how many independent measurements were there in that thing. And then it's just the usual error analysis that you know, the error in the thing is the square root of the variance over the number of measurements. And that number of measurements is proportional to time. So it means that your error bar is going to go down like 1 over the square root of time. And you know, that's unpleasant, but that's the way it is.
Yeah,
So
totally get it. Yeah.